tally the actual forces on the left-hand side and the required force on the right. Okay, and when the problems get more complicated, this is important. Okay, then many wrongs make a wrong instead of a right, and you get the wrong answer if you don't know how to keep this correctly. Now, I think the common instinct to have an outward force comes from something called centrifugal force. So I should say a few brief words about that before the next example. So you may have heard of this before, centrifugal force. Not to be mixed up with centripetal, we're talking about centrifugal. So this is this kind of outward force that you feel. You feel like you're getting pushed out of a circle when you are going in a circle. So outward force. And I'm here to tell you, as real as it feels when you're taking a turn, it doesn't really exist. Okay, so let's talk about why. So here's you in your car, and you decide you're going to take a right turn. It sure feels like you get thrown, your left shoulder feels like it gets thrown on the driver's side door. Okay, so what's really going on? Well, if you decided when you were taking a right turn to take off your seatbelt and open the car door, yes, you would fly out the door. That's not because of a force. That is simply because of your body's own inertia wanting to go in a straight line because you don't have a force. Okay? So there's no outward force. It's the lack of a force which causes you to go out of the circle in a straight line. It's actually the car door pushing you inward to hold you in a turn. Okay? So there is no outward force. There's an inward force, and that's the centripetal force. You're, of course, not used to the car door pushing on you. Okay? So you see it as you're getting pushed toward the car door. Okay? You're really just not used to feeling in a state where you're this long experiencing inertia, this idea that you don't want to be changing your motion. But that's all a turn is. A turn is continuously being asked to do something that you would rather not continue to do. You don't want that motion to change, and yet a circle is continuously changing it. So the car door exerts it, and your seatbelt exert an inward force on you. It feels uncomfortable. You perceive it as an outward force, but again, there is no outward force. It is simply that in the absence of a force, you would go out of the circle in a straight line. Okay? So the centrifugal force does not exist. Okay? You hear people talking about it, but it does not really, it's something that is more of a perception rather than an actual thing. You can do lots of crazy mathematics with it and even kind of make it come out on the math and treat it as like a real thing, but ultimately it's not consistent with Newton's laws. Okay? Are there any questions on that before I move on to the next example? Okay, so let's do another example where we have multiple forces teaming up to contribute to the centripetal force, to meet this requirement. This one I'm not going to sketch out quite as fully, but let me kind of just talk through the situation. Now we're back on Earth, okay? And we're swinging a bucket in a vertical circle. Guess I can draw a person. Let's put some water in the bucket while we're at it. If you ever tried this, it's good times. Okay, you swing the bucket, and at the top, the water doesn't fall on your head, right? So let's talk about why that works. Okay. So, also want to talk about what's going on at the bottom. Good practice. So first of all, let me go ahead and acknowledge, I'll call it the point at the top, point 1, and I'll call the point at the bottom, point 2. And I do want to acknowledge something that may already be obvious. This speed does change, okay? So the speed of the bucket will vary. Now I can talk a little bit on why that is. You probably can reason through the fact that at some points during the circle there will be tangential force, and tangential force will change the speed. I'm not going to bother too much right now with that, because we'll find that there's some great ways when we get to the energy method to calculate how much the speed changes. It's not really worth it right now. But right now I just want to acknowledge the fact that the speeds are different. Okay? I'll just call them V1 and V2 and go from there. Okay? But that's one of the reasons why I don't want to get too numerical here, just because there are a few things that we can't really talk about the system quite yet. So let's take a look at the forces that are going on at each point. I guess let's start with the top. So tension always pulls, never pushes, so tension points down, T1. And then since we're on Earth, what other force should we consider? Gravity. And gravity points which way? Also down, because of course it's always down, right? So there, the rules of thumb for those two forces lead them to both act the same way. Let's do the bottom. The tension always pulls, so that pulls like that, so the tension is always radially inward. And the force of gravity, of course, is always down, so now the two forces are actually acting in opposite directions. All right? So let's talk through each point. Let's do the force balance. Let's start with point 2. Now with point 2, notice that there are forces both up and down. So here we might be careful to choose a positive direction. I'll go ahead and choose upward to be positive. I'm going to put the actual forces on the left-hand side and set them equal to the requirement on the right-hand side. So I have T2 acts up, gravity acts down, and then the required force being toward the center, well now toward the center is plus, okay? So what we have is two actual forces, tension and gravity. One acts up, one acts down, but we know overall the winner, the imbalance has to be up because that's toward the center, right? Whenever you're doing the circle, you have to have force toward the center. So for instance, if we wanted to, and this is V2. So if we wanted to calculate the tension, we could. T2 is equal to mg plus mv squared over r. And to point the perhaps obvious, the tension has to exceed that. The tension has to exceed the weight. If you want an upward force overall, which you have to because you're in a circle, upward force has to beat the downward force. So for instance, if you found, I don't know, this might be easier. What if you needed 10 newtons toward the center? Just for example, right? Based on your mass, your speed, and your radius, you needed 10 newtons toward the center. If gravity was pulling 8 newtons away from the center, how much does tension need to pull toward the center? How do you get 10 newtons up when you have 8 newtons down? You need 18 up. The tension has to exceed the weight. If you need any more evidence of this, there's lots of YouTube videos that you can look up of people failing spectacularly on a rope swing. Okay, so they climb some big tall tree and grab onto a rope and they try to swing down through the bottom and then mayhem. Okay, here's why. Okay, if you're just hanging from a rope, the tension and gravity just need to balance. Okay, but when you hit the bottom of that swing, going who knows how fast, the amount of force that is needed to hold that turn is very large. And so your tension has to exceed your weight, okay? And of course, what happens is a lot of people don't realize that. They think, oh, I can just hang on a rope. Well, that's good enough. I'll climb into this 50-foot tree and then try to swing down through. But the faster you're going, the more tension, the tension that you may need to generate, maybe many times your own weight. And of course, what happens when someone can't generate that tension is they go off the rope, right? And they fly off. What do? They fly off more or less in a straight line, right? They don't swing up. They go skidding along the bottom there, okay? So that's a little bit about swinging through the bottom. Are there any questions on that before I move on to the top? Okay, so let's do the top. Now I could certainly go ahead and keep the same positive axis, but then it'd be annoying because everything would be negative. So let me go ahead and not be too afraid to set downward as positive. At this point, hopefully you realize that it's just a reference. There's nothing really truly positive or negative out in the real world. So then on the actual forces side, I have the duo of two forces acting together. They're both acting inward, and that is what provides the required inward force. And notice that again, mv squared of r is toward the center, and that can again be encoded by a plus sign. Okay? So we have the dynamic duo of the tension and gravity working together. They're going to provide whatever amount of force you need. Okay? They're not now opposed, they're working together. So let's take a look at some examples. I think it's easier if we go numerical. Let's say you need, I don't know, let's say 15 newtons toward the center. And let's say, for instance, that the force of gravity is 5. Okay? Well, gravity alone can't cover that. If you need 15 newtons toward the center, gravity provides 5. What does the tension need to kick in? It needs to kick in 10. And assuming the rope can not break at 10 newtons, then you get to go in a circle. Okay? That's when you're going really fast. You feel a lot of tension in your arm because at the top you have to pull down too. The force of gravity is not enough. You have to pull down too. Because if you can't supply that force, it flies away. For instance, if you're going like this and you accidentally let it go at the top, when it's going really fast, it's flying away. You're not worried about the water falling in your head, you're worried about the bucket going over there. Okay? Let's slow it down. Okay? So if we decrease the speed, we're going to decrease the amount of force necessary. Let's say we only need, I don't know, 7 newtons. Well, gravity puts in what it puts in. This thing has a certain weight, right? 5 newtons. How much does tension need to put in now? 2 newtons. Just needs to cover the extra. They're working as a team. But notice that when they work as a team, gravity puts in a flat rate amount, okay? Gravity always puts in what it puts in. In my case here, 5 newtons. Tension always has to cover the rest, okay? Tension is the thing that can adjust. It can change the amount of tension that's applied. It's like if you have a friend and you're going out to dinner, right? You guys are going to split the check, okay? So there's a certain required amount for the bill, right? If your friend always puts in $5 for dinner, you usually don't, you probably wouldn't want to take him to expensive dinner, okay? Right? Because then you're going to have to put in way more. So if you take a McDonald's or something, okay, then $5 covers most of it, you just need to cover a little bit, okay? So tension and mg work together, but mg always puts in a certain amount, and then tension needs to make up for it, okay? Let's go down, let's slow down even more. Let's say you only need 5 newtons to hold this turn. Well, gravity puts in 5 newtons already, so what's the tension? 0, okay? Your friend always puts in $5 for dinner. If you go somewhere where dinner is $5, you eat for free, right? Okay. What about, though, if we only need 4 newtons? How is that going to work? Can we make this equation balance? We can't, right? The tension can be 0 at the least. It can't go negative. And gravity, you can't do anything about it. So if you do that, this equation can no longer match. That doesn't violate the laws of physics. It just says you can't go in a circle. Because what happens if the actual amount of force toward the center is more than required? What happens to the circle? It collapses inward. And that's exactly what the water does. It falls on your head. Okay, so for this, you're going to collapse inward. So if you swing a bucket slow enough, it'll collapse inward. It won't fly away. Now it's going to fall on your head. Okay? So we back it up a notch. When was the last time we could have satisfied the equation? Well, V goes to V min when the tension goes to 0. Okay? So what I'm saying there is that the slowest speed that you can successfully navigate the circle is such that the amount of force you're needing is already met by gravity entirely, and the tension doesn't need to do anything. Okay? So essentially what you're saying is you're going so slow that gravity can cover the amount of force necessary, and the tension doesn't need to do anything. Okay? So you can try it yourself. Swing a bucket like this with water in it, slow it down, and slow it down, and you'll find at some point your arm is just limp up here. It doesn't need to pull anything. The reason why the water stays in there is gravity is what is just giving you the centripetal force to go like this, right, to make the turn. It's not yet collapsing the circle. Gravity alone is able to cause the motion to curve like this. Okay? So if you're going as slow as possible through the top, the tension is 0. But of course, if you're going faster than that, then tension still needs to kick in some extra. Okay? All right, so I've talked through that example. We'll do some more on Thursday.